it's only you yourself internally who can definitively, have something to say about what conscious experience is. So I'm fighting with on this issue, and I don't think I'm not saying there isn't an answer, but I don't think you've given it, which is, how do you define success? In other words, let's say I'm going to, that question of how do you define success, you have rather dismissively said that my friends, the LLMs, are all, merely, they're merely sort of regurgitating the things that went into them, so to speak. But you claim that, we are not, so to speak. But so my question will be, if you can define a notion of success for consciousness as experienced by you and as extrapolated by you, as experienced by me and other humans and so on, then the question is, what, that definition of success of did you manage to derive that? Is that definition of success transportable enough that I can really apply it to an LLM? And perhaps the answer will be, the LLM is not conscious. But right now, you haven't given me anything that is concrete enough that I can take it and fit it onto the LLM and say, do you win or do you lose?
Right. So I owe you a mathematically precise theory of consciousness, a scientific theory of consciousness that could try to do that kind of thing. And
perhaps.
That's what we're trying to do. We have a theory we call the theory of conscious agents, and we have some papers that we've published where we have a mathematical model. It uses Markovian dynamics in the model. And what we're doing right now, is to try to answer your question, right? So I agree with you. What you're asking for is exactly what we have to do. And the way we're going at it is as follows. The high energy theoretical physicists in the last 10 years have discovered these positive geometries beyond space-time and quantum theory. And behind those positive geometries, they found these combinatorial objects that classify them. They're called decorated permutations. And so this is just in the last 10 years, but so we've taken off the headset, the space-time headset, and we've gone outside for the first time, and we're finding these obelisks, these positive geometries outside of space-time and these combinatorial objects. So what we're doing to actually respond to your question is we're saying, let's start with a mathematical model of consciousness, qua consciousness. So it's like a network of interacting conscious agents. So it's a social network, and it's governed by Markovian dynamics. And what we're doing then is saying, can we take this Markovian dynamics and first show that we can project onto the decorated permutations that the physicists have found, and then from there project onto the positive geometries? If so, then we can project all the way into space-time, and then we would actually be able to make testable predictions inside space-time from a theory that says consciousness is fundamental, and we start there. So we published a paper last year where we actually showed some new mathematics apparently about Markovian dynamics, and we showed how they can be classified with decorated permutations. So we published that. And now what we're doing is we're trying to show that we can get the positive geometries, like the amplituhedron, as projections of Markov polytopes, which are the spaces of all possible Markovian dynamics. So what you're asking for is exactly what should be asked for. And what we're trying to do is to show that we could get all of physics, plus more, from a theory of conscious agents being assumed to be fundamental outside of space-time, and projecting through decorated permutations, positive geometries into space-time where we can make our empirical tests. So that's what we have to do. But if we don't assume that consciousness is fundamental in the foundations of our theories, then we either have to dismiss consciousness and say it's not there, or we have to give a theory in terms of unconscious entities about how consciousness emerges. And if we try to do that last, I claim that it's not logically possible to start with unconscious ingredients and to have consciousness emerge. Not possible.
See, that is not my intuition. Okay? I mean, you and Leibniz have the same intuition. I think the reason I disagree with Leibniz's intuition, if you'd asked me in 1980, do I disagree with Leibniz's intuition? I would have said, I don't know. I don't know how you would get a mind-like thing to arise from a non-mind-like sort of origin. But then, by 1981, I was starting to do all kinds of computer experiments and so on about what simple rules can actually do.
Right.
And it really surprised me. In other words, what could emerge from something that seemed like it was too sterile to generate anything interesting, I was completely wrong. And it's amazing that even after all these years, I do these experiments on different kinds of systems, and I keep on being wrong. And I keep on thinking, this thing is somehow too simple to do anything interesting. And my intuition keeps on, even though I think I've now developed much better intuition about this, it is remarkable the extent to which sort of things, much richer things than you might imagine, can emerge from simple causes, so to speak. And so I think that's a foundational kind of piece of intuition that I've developed. It's kind of fun for me because this idea of computational irreducibility that I actually introduced about 40 years and a week ago. It is interesting to me that when I talk to some younger scientists and so on, for them, computational irreducibility is obvious. The world could not be any other way, and which is how I feel about it too.
Right.
But it's a thing where if you grow up with this idea, it's kind of an obvious idea in the end. It becomes obvious after you've kind of ground on it enough. But right. I think that idea was something certainly not known. That's a new piece of information, a new piece of sort of intuitionally relevant information. So that affects my thinking about this.
Correct me if I'm incorrect, Don. I don't think you're disagreeing with what Stephen just said. Stephen, what you had said is that, look, we can start with something that's simple, mechanically simple, and then get to something that is extremely mechanically complex, such that we would never think, looking at the complex case, that it could be made of these elementary elements. And Don is saying, that's correct, but notice the word mechanical there. You can get something that's simple mechanically and give rise to something that's complex mechanically, right. But that's a different question than jumping ontological categories.
Right. So the claim is that there's a spark of consciousness that can simply not be reached mechanically. That's the claim.
That's the claim.
And, right. So, okay. So it's an interesting claim. It's a claim that I think the structure of the science that we have is not going to be able to talk about it. In other words, you can say, let's turn science on its head, and let's say that's our basis, and then let's see what we can construct about the rest of science. That's a perfectly intellectually valid thing to do. But if you're going to ask, given the fact that you're not able to give a kind of a science-based definition, you're not going to be able to get to what you want from kind of, you might very well be able to, as I keep on saying, from a theory in which all that's real is what observers observe, mm-hmm. I have no doubt that you can go from such a theory to deduce how things have to work in the world, and even to be able to say, given this way of how things work in the world, we could come up with kind of a sort of a meta theory that corresponds to space and time and all these kinds of things, that is a good description of what we have derived from this underlying theory that starts with observers. Actually, I want to ask something about that in what you described. Mm-hmm. Do you think that there could just be one observer? In other words, do you think it's important to the nature of observers that there are many of them and that they have some correspondence to each other? Or do you think that if in fact it was the case that, you were the last human alive and there's no other sort of, I don't know what, I don't think intelligence relies on life forms, but imagine that it did, and you were the only thing in the universe that was like you and quotes conscious. Is that an okay situation? Or is there something that would not work in your theory? Would your theory require that there's a whole flock of observers there?
Yeah, so it's quite striking that the paper we're writing right now, that we'll be publishing hopefully later this year, we've discovered a new logic on the space of Markovian kernels. So we're able to associate a Markovian kernel to each conscious observer. And the Markovian kernel is basically describing, given that my current experience is red, what's the probability the next one will be green, and so forth, and you can write down a matrix of it. It's what we call the qualia kernel. And
I think there's a horrible problem with that, but we'll come to that in a minute.
Well, okay, sure. But so then there's the question, can these conscious agents and the Markovian kernels combine to create new conscious agents with more experiences? And we discovered, we'll be in this new paper announcing a new logic on Markovian kernels that we just discovered. You probably know about taking a Markovian kernel and taking a trace chain on a subset of states.
I can immediately imagine what that means, but yes.
Yeah,
okay.
yeah. So if I have a 10 by 10
I get it.
and I only look at 3 of the states, it's going to induce the dynamics on the 3 by 3, and you'll get a new kernel on the 3 by 3 kernel that's induced by the 10 by 10. It's called a trace chain. So it turns out what we're going to publish is that the one kernel being the trace of another gives you a partial order on all kernels. So it turns out that's a partial order.
Sure.
And so it actually, for example, the trace of a trace is a trace. So it's transitive and irreflexive and so forth. So it's actually, it gives you a logic, and it gives you a logic about with an least upper bound, a greatest lower bound, and so forth. It turns out it's a non-Boolean logic of these Markovian kernels.
Okay.
There's no top. There's no top consciousness. There's an infinite number of directions that you can go infinitely far in terms of combining. It's locally Boolean. So if I take a particular Markovian kernel, all the kernels that are less than it in this logic form a Boolean logic. So it's locally Boolean.
So just a technical question here. I mean, so these, we can think of one of these Markovian kernels as defined by some matrix, okay, so are these finite matrices or are these infinite matrices?
Well, right now, what we've been doing are finite, but in this paper, we're only going to deal with finite. We'll then look, at the continuous case and so forth beyond that.
Okay, so I mean, what you're saying is, given that I have a probability matrix that says, your Markovian matrices are kind of like random versions of S matrices in a sense that they're saying, given this vector of what comes in, this you multiply by this matrix and you get this vector of what comes out. And you're doing that purely in terms of probabilities. But now what you're saying is, given I'm just trying to understand the technical aspect of what you're describing, given such a matrix, you are saying there are you can extract submatrices by tracing out for anybody who's watching this who wants to know what that actually means, it's you're just adding, you're getting rid of those components by just adding up a bunch of things and fixing right. What happens. So we've got, some part of our matrix is still flapping around, free as a bird, so to speak, and another part has been locked down. And what you're saying is, if in all the different forms of locking down, they form they're kind of like subsets of a set or something. They form some kind of partial order of, you lock down this, and that there will be pieces that are in, you can lock down this part, and if you lock down a part of that part, it's sort of it's a proper subset there, and you can have another part that is sort of that's right. Yeah, I'm going to start spouting technical things about chains and anti-chains and so on, but which is probably not very useful, but at least helps me understand what's going on. Okay,
that's right. But by the way, most Markovian kernels are not comparable. Right. So if you give you a Markovian kernel,
absolutely,
almost every Markovian kernel is not greater than or less than it. Right. It's quite an accomplishment to have any kind of relationship at all with other Markovian kernels, which gets at the diversity of consciousnesses and the relationship. But it turns out you can't combine consciousnesses unless where the states overlap, they have the same trace. You have to have the same trace on your overlapping states to allow consciousnesses to combine.
I'm hoping that there's more to consciousness than Markovian matrices. Well, because that's a shockingly minimal kind of view of what, and also to say, I'm never a believer in theories that have probability as a fundamental component.
Well, so there's two things there. So the first, though, I would bring up something called the theory of computational equivalence.
Yes.
that I agree with you on. And it's a simple thing to point out that Markovian kernels are computationally universal. It's trivial. So
Right, but
even,
the problem is, as soon as you've got probability in the picture, you're no longer dealing with pure computational rules. Probability is a statement. I mean, you can, if you're looking at the manifold of all possibilities and you're just viewing probability as a way, as a parameter, effectively, to sort of sample your space. So, for example, let's say I say I've got a circle. Okay, there's a well-defined meaning to, or a disk, let's say, a region that's circular. And then I say, well, actually, I don't have a circle. I just have this probability distribution that allows points to be dropped anywhere in this region. Now, I could describe the circle by saying that I have this probability distribution that, in mathematical terms, only has support within the circle, only has a non-zero probability within the circle. That will be a way of describing the circle. But if I am to talk about the sequence of points that are dropped in the circle, then I've got a whole bunch more. It's no longer sort of accessible to pure computation. As soon as I can drop the points according to probability, I don't have a rule for where the points will land.
Well, but there's a theorem in automata theory that the non-deterministic automata, Turing machines, for example, have exactly the same computational class as the deterministic. There's not something.
That's a much more detailed issue. Let's unroll that. That's not correct. In okay. Deterministic and non-deterministic Turing machines absolutely have the same computational power. But that is not the same statement as that a probabilistic Turing machine has the same kind of computational character as a Turing machine. Let's unpack that.
Well, it may have a different character, sure.
Right, but let's unpack that. We've got a Turing machine. A Turing machine has definite rules. You start it from some initial state. It goes crunch, 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 and generates, its succession of states. But now let's say it's a probabilistic Turing machine. And that means that what it does at every step is not definite. It's determined by some probability, but it does something. It's just we don't know what it will do, and it has a probability of 30% of doing this and 70% of doing that. Mm-hmm. But at every step, it does something, right? So that's the probabilistic Turing machine. We don't know what it does. It's going to do at every step, but at every step, it does something. Right. A non-deterministic Turing machine is a different story. A non-deterministic Turing machine is asking, what are all the possible things that could happen? We've got many paths of history. The Turing machine could go left, it could go right. We actually take all of those paths. We build up this whole, we call them multi-way graphs of all possible paths. Mm-hmm. Okay, and the statement is that if what you're interested in is, does there exist a path that leads to this or that thing? That's the full. Put it this way, the multi-way graph is computationally equivalent to the single-way Turing machine.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.